Well, hello again, class. It is that time, everybody's favorite time of the day, math time. So, we just learned how to do basic derivatives without using the difference quotient. Yay, shortcuts! And now it's time for us to see what are some of the real world uses of derivatives because they have real world value. So, this lesson is called Velocity and Other Rates of Change. It focuses on where things are, which direction they're moving, how fast they're moving, and if they're accelerating, how much total distance they've covered. Basically, it's the math of motion. So we begin with displacement. The displacement function, unfortunately, is denoted with lowercase s of t, and I say unfortunately because it's kind of hard to tell the difference between a lowercase s and an uppercase s. Anyway, s of t, lowercase s of t, is a displacement function. And for any value of t for time, it's going to give us the displacement from the origin, meaning how far from the origin is it and in which direction. Positive, you know what, we'll get to that in a moment. Now, velocity is all about the change in position and at what rate. See, there's that word again, rate. So velocity clearly has something to do with a rate of change, aka slope, aka derivative of displacement. First, let's talk about average velocity. It's just an average rate of change. It's all it is. So the average velocity is the average rate of change of the velocity function. Anyway, the average velocity of an object moving in a straight line from time t1 to time t2 is legitimately just the slope formula. y2 minus y1 over x2 minus x1. But of course, instead of x's, we're using t's, and instead of y, we're using s. But it's legitimately just the slope function, average velocity. Well, the instantaneous rate of change, which means the slope at any single point of the displacement function, is the first derivative of the displacement function. So if lower s of t is the displacement function and it's moving in a straight line, then velocity, little v of time, is equal to s prime of t. Here's the difference quotient. We're not going to use it. We're going to use the stuff that we learned in lesson 3.3. Anyway, again, the velocity function is the derivative of the displacement. And it should make sense because the velocity is the rate of change of position. It's called the instantaneous velocity or just the velocity function. And then acceleration. Acceleration is the rate at which we change our velocity, which means it's the derivative of velocity, but I'm getting ahead of ourselves. So if an object moves in a straight line and the velocity function is v of t, then the average acceleration, just like the average velocity, is nothing but the average rate of change of the velocity function. From t equals t1 to t equals t2, then it's legitimately just y2 minus y1 over x2 minus x1, again where our x's are t's for time and our y values are velocities at that time. The instantaneous acceleration, meaning the slope at any given point, is the velocity derivative, and that should make sense because it's the rate at which velocity changes, rate of change, derivative. So, sum it up. The too long didn't read. First derivative of displacement is velocity. Second derivative of displacement is acceleration. Therefore, the first derivative of velocity is acceleration. Here it is in symbols. Velocity, v of t, is s prime of t. Acceleration at any point, at any time, is v prime of t or s double prime of t. A little bit of new information. S of 0, v of 0, and a of 0 tell us what's going on when time is 0. So it gives us the position, the velocity, and the acceleration of a particle at time equals 0. These are called the initial conditions. So where did you start? What was the velocity when you started? And what was the acceleration when you started? So we flip it over for some more just information. Sign diagrams are going to give us the entire story of what's going on. And in case you don't remember what a sign diagram is, A sign diagram is one of those things where we're drawing ourselves an x-axis, which would now be a t-axis, and we'd be finding, specific critical values, and then we'd be doing things like, oh, positive, negative, positive. The sign diagrams, okay? So if you drew a sign diagram for displacement, S of t, position, what does it mean if S of t is equal to 0? That means you're displaced 0 units away from the origin, therefore point P is at the origin. What if you have a positive displacement? That means you're to the right of the origin. And a negative displacement to the left of the origin. Okay. So if you get a sign diagram for velocity, what does it mean if velocity of 0? That means that your particle at that moment in time is at rest. A velocity of 0 means you are not moving or changing directions. If you have a positive velocity, that means your particle is moving to the right. And if you have a negative velocity, then you are moving to the left. And acceleration, being the rate of change of velocity, well, if you have an acceleration of 0, that means that the velocity may be a maximum or a minimum or just a constant. Why a maximum or a minimum? Because if the curve looked like this, right here I have a horizontal tangent, and right here I have a horizontal tangent. So their slopes are 0. So that curvy cubic that I just drew, if that was my velocity graph, then these are flat places. So they have a slope of 0 there, which means we have no acceleration. If your if your acceleration is positive, that means your velocity is increasing. And if your acceleration is negative, that means your velocity is decreasing. And speed. See, speed is not the same thing as velocity. Velocity is speed and direction. Speed has no direction. So the speed is the magnitude of the velocity, meaning the absolute value of the velocity. And we use capital S for speed, lowercase s for displacement. I know, it's terrible, but it is what it is. So how do you know when your object is speeding up or not? Well, with your sign diagrams, if you find that your velocity and your acceleration have the same sign, meaning they're both positive or they're both negative, then your object's speed is increasing. If they don't have the same sign, they're opposites. One's positive and one is negative. That means your speed is decreasing. And that should make sense, because let's say I have a positive velocity, that means I'm heading to the right, and I have a positive acceleration. That means as I'm heading to the right, I'm going faster and faster and faster. Therefore, my speed is increasing. Now, if my velocity was positive, meaning I'm going to the right, but my acceleration is negative, what that means is, yes, I'm still heading to the right, but the rate at which I'm leaving the origin is slowing down and slowing down and slowing down. Eventually, it would come to a dead stop and start heading back towards the origin. So even though I am still heading to the right, a negative acceleration would be slowing the rate at which I'm moving to the right, which means my object's speed must be decreasing. So that was a lot of talking. It's time to actually do an example. One example to be exact, with a lot of parts. And it's basically going to take up this whole page. So don't write large. Okay, so we got a particle that's moving in a straight line. Its position, lowercase s of t, relative to the origin is given by t cubed minus 3t plus 1, where t is the time in seconds. And of course, we don't have time machines, so time is greater than or equal to 0. Okay, so it says find expressions for the particle's velocity, acceleration, and draw sign diagrams for each of them. Okay, part A says velocity. Well, velocity is s prime of t, the derivative of displacement. So the derivative of this, and we're just going to use our power rule. Bring the 3 down to the front, decrease the exponent by 1, and then right here, this is linear. The slope of every linear is the number in front of x, in this case t, so it's just going to be minus 3. There. That is our velocity function. You know what? I think factors. Well, we're going to have to figure out what its critical values are, and its critical values are going to happen when you set it equal to 0. So let's pull a 3 out. Gives me t squared minus 1, which is the difference of two squares. So t plus 1 times t minus 1. Oops, I forgot. Well, we'll just call that a t minus 1. There. So the velocity has two critical values. One at time equals -1, which makes absolutely no sense, and the other one at time equals +1. So again, we don't have time machines, so negative time makes no sense. Time for the sign diagram. Starts at 0. This is our t-axis, if you would like to call it that. All right. So what we need to do is figure out what was going on. I wrote t. Figure out what was going on between times 0 and 1, because 1 is the only positive time we got as a critical value. So let's plug in a number like 0.5. And I'll plug it in here because it makes life easy. 0.5 plus 1 is positive. 0.5 minus 1 is negative. 3 times positive times negative gives me a negative. And then after time equals 1, like 2. 2 plus 1 is positive, 2 minus 1 is positive, and times 3 is still positive, so everything's positive. Boom. All right, now let's find our acceleration. A of t would be v prime of t. So looking for the derivative of this. Again, power rule. Bring the 2 down to the front, gets multiplied by the 3. You get 6t. And the derivative of this constant is 0. So well, the only time that's ever equal to 0 is at time equals 0. So it has one critical value, and it happens to be when our domain begins, when time equals 0. And you could plug in any positive number you want right here. 6 times positive number is positive. There. So we have our velocity function, our acceleration function, and we have sign diagrams for both. Part B says to find the initial conditions and to describe the motion. We're going to find those initial conditions as values, and then we'll just discuss what they mean. B. What is little s of 0? Well, if we plug in 0 everywhere we have a t up here, that's 0, that's 0, and we're just left with this 1. Now let's figure out what our initial velocity is by plugging in a 0 here. That gives you all this is 0, you get a -3. And let's find our initial acceleration, which is kind of hard to think about, but we'll plug it in anyway. Plug in 0, you get 0. So interpretation, what does this mean? It means we began 1 centimeter, because the units we're working with in this question, centimeters, 1 centimeter to the right of the origin. And the moment we started moving, we were heading left at 3 centimeters per second. And our acceleration was 0, and that should make sense because how do you have acceleration at an instant when your domain begins? So hopefully it makes sense why that is true. Part C says describe the motion of the particle when time is 2. So for part C, we're going to do the exact same thing, but we're going to plug in 2 instead of 0. So what is little s of 2? Well, it's 8 minus 6 plus 1, which is 3. So after 2 seconds, we're 3 units to the right of the origin. That's interesting because when we began, we were 1 unit to the right, but we were moving to the left. I must have turned around somewhere. What is our velocity at time equals 2? It's 3 times 3 times 1. And what is our acceleration? Well, it's just 6 times 2. So it says to describe the motion. At 2 seconds, we're 3 units to the right of the origin. We're moving to the right at 9 centimeters per second, and we're accelerating at 12 centimeters per second squared. Okay, part D says find the position of the particle when changes in direction occur. Well, D. Changes directions at time equals 1. How did I know that? my sign diagram. See, my velocity says between the times of 0 and 1, I was heading left. And then after the time t equals 1, I was heading to the right. Clearly, I turned around right here. So what is S of 1? Where was my position? Well, it's 3 times 1 minus 3. Excuse me. Position. Sorry, that's velocity. There we go. I'll be okay. Plug in 1 here. 1 minus 3 plus 1. That equals negative 1. So at time equals 1, I was 1 unit to the left of the origin, and that's when I started heading to the right. It was right after that instant in time. E. E says to draw a motion diagram for the particle. Now remember, this particle is just moving left and right, which is technically one-dimensional. Left and right is one dimension. What I'm going to do is I'm going to impart an up and down just so we can actually see the particle moving. It doesn't mean that it actually went up and down. It's just the way that I'm going to draw it, so it'll make more sense. So here we have a position axis with our origin being somewhere around here. Okay. T values that did things for us were time equals 0, time equals 1, and we were specifically told to figure out what was going on at time equals 2. But these don't go on here because this is a position diagram. So let's say I got negative 1, 1, 2, 3. These are just distances from the origin. So at time equals 0, our position was positive 1. So we were right here at time equals 0. Nothing special happened between time equals 1 and time equals 0 and time equals 1. See, right here at time equals 1 is when we turned around. But our position at time equals 1 was negative 1. That's where I was after 1 second. So I was heading this direction like this for the first 1 second. The next time that mattered to us at all was time equals 2, because that's what we were told to plug in. At time equals 2, our position was positive 3. And we continue to head to the right forever after that. So that is our motion diagram. See, we didn't actually go up and down. What actually happened was the particle did this. It started here and then went to here and then put the brakes on it and then went back this way. But you see, just tracing over the x-axis, you can't see where it turned around. So we draw it like that and just kind of stretch it out this way just so we can see what the motion was doing. Part F. It says, for what time interval is the particle's speed increasing? Well, remember, speed is only increasing when velocity and acceleration have the same sign. Well, acceleration is always positive. So where did they have the same sign? When velocity was also positive, meaning after time equals 1. So for time greater than 1, we can't say or equal to, because at time equals 0, this number is, the velocity is 0, and time equals 1, our velocity is 0, which is not a positive number. So we have to say after the first second. So for time is greater than 1, our particle is speeding up. And last but definitely not least, what is the total distance traveled from time equals 0 to time equals 2? That means how much distance did we cover in the first 2 seconds? FG. Well, between 0 and 1 second, distance is, this was time equals 0, This is time equals 1. I clearly move to the left 1, 2 units. And then from 1 to 2, I went all the way back 1, 2, 3, 4 units to the right. So total is 6. 2 steps left, 4 steps right. And there it is. If it was a little bit confusing, I understand. I'm sure there's a million videos out on YouTube that you could look up if you really wanted to. As far as I'm concerned, mine's the best because I am the best. But, sometimes my wife is laughing at me. Anyway, sometimes it might help to hear other people say it and do things slightly different. So if you were trying to see some other notes, the word that you would be looking for is kinematics. That's what this is called. Okay? All right, folks, that's all we have for today. So I hope you're doing well. I hope that everything is going smoothly with your other courses. And should you need me for anything, hit me on my mind. Talk to you later.